Here's a thing that ought to be flatly impossible, and I've come down tonight to make you admit you were pulling my leg. For the first few minutes of all of time, not somewhere, mind you, but everywhere, every last corner of space at once, the whole universe was a furnace, hotter than the middle of any star that will ever burn. And in that furnace, in about the length of time it takes to boil an egg, it cooked very nearly all the hydrogen and all the helium there would ever be, and then the oven slammed shut and never opened again. That's the sentence you left me holding last week. I've decided it's a fairy tale. So, talk me out of the decision.
I'm not going to talk you out of it. I'm going to make it worse. Because I was gentle with you last week, I left a word out to be kind, and tonight I'm putting the word back in.
Oh, that's ominous. You were being kind. Which word did you spare me?
Everywhere. When I say the universe was a furnace, I don't mean there was a furnace glowing away somewhere off in the dark. I mean every scrap of space you can point at, the space your chair sits in right now, the space out past the last star. All of it, at the same instant, hotter than a stellar heart. There was no cool spot to stand in, no outside. The furnace was the whole of everything.
Right, that's the thing you drilled into me 2 courses running. The Big Bang wasn't a bomb going off in a room, it was the room. Everywhere, all at once.
It was the room, everywhere, all at once. And in the first few minutes, hot past all imagining. Hold on to that, because the whole of tonight hangs off it.
Give me a feel for past all imagining, though. You keep saying hotter than a star's heart, and I'll be honest, I can't picture a star's heart to begin with, so I've nothing to be impressed against.
Fair? Then don't picture a temperature at all. Picture what the heat forbids. It's hot enough that nothing can hold a shape. An atom is a fantasy. Even the hard little knot at the heart of an atom is a fantasy. Nothing gets to be a thing. All you've got is a blinding sea of light and a fog of loose pieces tearing through it, and every piece slamming into every other piece harder than you can hold in your head.
A sea of light with the crumbs of matter thrashing about inside it. And that's not one white-hot spot in the sky, that's the entire sky, and the ground, and me.
The entire everything. And this is the part I want honest between us tonight, because it's tempting to slip into thinking of it as a place. It isn't a place. It's a condition the whole universe was in at the very same moment, top to bottom. There was nowhere it wasn't.
All right, and you keep saying the first 3 minutes, which is a lovely round-sounding thing to put on a poster, but is it really 3? Or is 3 just the number that scans nicely?
3 is a fair sketch of it, no more. The honest thing to say is minutes. A small handful of minutes. And the reason that's the astonishing bit isn't the exact count on the clock. It's the word minutes, standing where you'd expect the word ages. The whole business is over before you'd have thought it had properly started.
Minutes where you'd expect ages. Fine, I'll stop haggling over the number, but let me get my bearings because last week you sat me down in front of a photograph, the oldest light there is, the baby photo. The glow that broke free when the fog cleared and the first atoms formed. Are we back at that same moment tonight?
Earlier. Much earlier. That baby photo is late in tonight's story. It's the moment the dust had already settled. The atoms forming, the fog lifting, the light streaming out at last. All of that comes hundreds of thousands of years after the part I want to show you now.
Hundreds of thousands of years after. So the baby photo isn't the first page of the album. There are earlier pages.
There are earlier pages, and they're the wildest ones in the book. Tonight we go back before there were atoms at all, before a single electron could sit still long enough to circle anything. Back to when the very pieces of the atoms were still being forged.
Now, hang on. You keep saying before atoms. I always took an atom to be about as small and as basic as the world gets. What's even left if you take the atom away?
the pieces of it. Picture an atom for me, any atom you like. It's got a tiny, heavy knot right at its heart, and a haze of far tinier things flitting around that knot. The knot in the middle, we call that the nucleus. The flitting things around it, those are the electrons.
The nucleus in the center, the electrons buzzing round it, that much has stuck.
Good. Now turn the heat up. Turn it up until the whole world glows. The electrons are the first to go. They simply won't sit still. They get knocked clean off and go tearing about loose, and no atom can hold together in that. That's the fog we spoke of last week.
So the baby photo is the electrons finally coming home to roost. The moment it cooled enough for them to settle down and be caught.
The electrons coming home. That's it exactly. But tonight I want to go hotter than that and further back. Because if the electrons come loose when it's merely blazing, imagine what happens when it's fiercer still. Now even the knot at the center, the nucleus itself, can't hold. It gets battered apart into its own pieces.
The nucleus has pieces too, of course it does. You people never stop, do you?
We never stop. But this is nearly the bottom, I promise. The nucleus is built out of two kinds of building block, and in the first minutes, that is very nearly all there was. Just those blocks, tearing about loose in the heat, with nothing yet built out of them.
Two kinds of block, hand them to me.
One kind carries a positive charge, call it the proton. The other is its slightly heavier cousin, and it carries no charge at all. Call it the neutron. A proton and a neutron are near enough the same weight, near enough twins, but for that one difference. The one is charged, the other is not. And tuck that little word, heavier, away in your pocket, by the way. The neutron being that shade heavier than the proton is going to come back and matter enormously before the night is out.
Proton, charged, neutron, not. And in the furnace they're just loose. A hot soup of the two of them.
A hot soup of the two of them, slamming into each other and into that fierce sea of light over and over, faster than you could ever picture. And now, here's the first thing I truly want you to see tonight. Tell me, what is a single lone proton?
You just told me. It's one of your two blocks, the charged one.
It is. But it's also something else, and this is the loveliest little secret of the whole night. A single proton, all on its own, is already a nucleus. The very simplest nucleus there is. It is the heart of a hydrogen atom.
Wait, so hydrogen is just a bare proton?
The nucleus of hydrogen, the simplest atom in all creation, is nothing but a single proton. That's the whole of it. So the furnace doesn't have to build hydrogen. Hydrogen is what you get for free. Every lone proton floating in that soup is already a hydrogen nucleus, sitting there finished, waiting only for an electron to join it ages later, in the baby photo.
So the most common stuff in the entire universe is the stuff the universe never even had to make. It's the default. The leftover block that never got built up into anything bigger.
You've run a whole flight of stairs ahead of me. But yes, that is exactly it. And by the end of the night, you'll see it matters more than anything else we say. Hydrogen is the block left over. Now, the interesting question, if a bare proton is hydrogen for free, what does the furnace actually have to sweat to build?
Anything bigger than one block. Anything you have to stick together.
Anything you have to stick together. And the very next thing up the line, the first real act of cooking, is to take those blocks and fuse them. Jam protons and neutrons together into a bigger knot that holds. Do it right, and you've climbed from hydrogen up to the next element. Helium.
Helium, the balloon gas, the squeaky voice gas. That helium.
That very helium. Though there's not an electron in sight yet, we're building only the bare heart of it. A helium nucleus is a tidy little bundle, 2 protons and 2 neutrons clamped together into one. That's the recipe. 2 of the charged blocks, two of the uncharged, fused into a single knot that holds.
2 protons, 2 neutrons. Doesn't sound so hard, honestly. You've a soup heaving with both of them all slamming about. Surely they just stick.
Ah, and there is the trouble. Because the charged blocks, the protons, do not want to stick. They shove.
They shove. The charge.
The charge. Two positives loathe each other, bring them close, and they push apart, harder and harder the nearer they get. To fuse them, you have to force them together anyway, close enough that a different, far stronger pull, one that only reaches across a whisker of a distance, can reach out, grab hold, and clamp them shut. It's a tug of war, in truth. The shove of the charge pushing out at every distance, and this other grip that stays silent until you're a hair apart and then seizes like a sprung trap. And the only way to force them across that last gap
is to fling them at each other hard enough. And hard enough means hot, doesn't it? Heat is just everything jostling and moving fast, so hotter means harder collisions.
Hotter means harder collisions. So you need it ferociously hot to fuse anything at all. Hot enough to slam those shoving protons close enough to catch. And the early universe? The early universe had heat to burn. This was the one moment in all of history when the whole of space, everywhere at once, was hot enough to force those hateful protons together. Never before. There was no before. Never again. The furnace was the one and only kitchen that could ever have done it.
Hold on, though. When two of them do finally stick, past all that shoving, does anything actually happen? Or do they just quietly clip together like a pair of magnets, and that's that?
Something happens. Something rather wonderful. When the blocks clamp into that snug helium bundle, the finished bundle weighs a shade less than the loose pieces did before they joined. A little bit of weight goes missing in the making.
Goes missing. Weight doesn't just go missing. Where does it go?
It leaves. As light and as motion, as heat. And that is the deepest thing Einstein ever handed us, that a little weight and a burst of light are two faces of the one coin, and one can turn into the other. So every single time the furnace fuses a helium nucleus, it pays out a small flash of light for the privilege. The cooking feeds the very fire that is doing the cooking. The furnace is not merely sitting in borrowed heat, it is partly stoking itself.
So the furnace isn't just sitting in the heat, the cooking itself is throwing off more heat. It's stoking its own oven.
Stoking its own oven. And keep that coin in your pocket, because it's the very same trick every star will run later to shine. Weight quietly turning into light. But that's a night for another week. Tonight the furnace is the cook.
Right, so we're fine then, surely. It's hot as anything, the blocks are colliding hard, helium gets built and throws off a bit of light for its trouble. Where's the catch? There's always a catch with you. I can hear it coming down the hall.
The catch is that the very same heat that lets you build a helium nucleus is hot enough to smash it straight back apart.
Oh, come off it. It builds it and unbuilds it.
When it's hot enough, truly, savagely hot, the way it was right at the start, nothing you fuse survives. You clamp two blocks together and the next violent collision knocks them straight apart again. The furnace is so ferocious, it uncooks its own cooking. Build, smash, build, smash. Nothing holds.
So the very hottest moment, the one you'd swear was best for cooking, is actually useless. It's too good at cooking. It cooks so hard it burns everything back down to raw ingredients.
Too good at cooking. I may steal that. Yes, at the fiercest heat, nothing sticks. So when can anything stick? Only once it's cooled a little. Only once the collisions have softened just enough that a newly built helium nucleus can take a knock and survive it, instead of shattering on the spot.
So I actually need the universe to cool down before anything I build will last. Fine, the universe is expanding. You spent 2 whole nights teaching me everything's flying apart and space itself is stretching. And stretching means cooling, surely. Spread the same fire thinner and it has to cool.
You've kept it. Yes, that expansion we watched, run forward from the fireball, thins the fire and cools it, second by second. It is a curious kind of clock that the universe does not cool because someone cracked a window. It cools because it is growing, and the same fire spread through ever more space simply cannot stay as fierce. So the furnace is cooling all on its own, all the time. Which sounds like pure good news. Wait long enough, it slides past the too hot to hold point, and the cooking can finally begin.
But I can hear a but from the far end of the room.
But the very same expansion that cools it is also thinning it, pulling everything further and further apart. And to fuse 2 blocks, they've got to actually meet. They have to find each other in the soup. Spread the soup too thin, and the blocks go sailing past one another in the emptiness and never collide at all.
Ah, so it's a vice. Too hot and nothing you build survives the next knock. Too cold and too thin and nothing ever meets to be built in the first place. And the universe is sliding straight from the one jaw into the other.
A vice. That's the word for it exactly, and it's closing. There's just one narrow band in the middle, cool enough now that a helium nucleus survives its knocks, but still hot and still crowded enough that the blocks are meeting and fusing like fury. A window. And nearly every helium nucleus the universe will ever hold gets made in that one narrow window as the furnace slides through it.
And how long does the window stay open? This is the boiling egg line, isn't it? You're about to tell me the whole thing is over in the time it takes to soft boil an egg.
A few minutes, that's all. The furnace passes through the sweet spot, cool enough, still thick enough, in a matter of minutes, and then the expansion has thinned it and chilled it clean past any hope of fusing another thing. The window opens, the universe cooks like a house afire, and then the window slams shut, and it never, ever opens again.
And that window, it opened when it did, and stayed open only as long as it did, purely because of how fast the universe was cooling. So the recipe itself is somehow tied to the expansion.
Tied to it, hand and glove. Had the universe grown and cooled even a shade differently, the split would have come out different. A different helping of helium, a different sky, a different chemistry, a different everything. The exact split we ended up with is pinned to precisely how fast this universe grew and cooled in its first minutes. So in a real sense, the recipe of all creation is a record of how quickly the young universe was flying apart. Change the expansion and you change the recipe.
The most important few minutes there have ever been. And they're done before the egg is.
Done before the egg is. Every light atom you're made of, every scrap of hydrogen in every glass of water you will ever drink, was settled in those minutes. The whole long history that followed never gets another crack at it.
All right, that one gave me an actual chill. But let me lean on the ratio because you keep saying mostly hydrogen, some helium, and I want to know why it isn't half and half. Or all helium. Why that particular lopsided split?
This is my favorite part of the night, so let me build it slowly. It comes down to the 2 blocks not being equals, not by the time the window swings open. And the reason they're not equal is the neutron.
The uncharged one, the heavier twin.
The heavier twin, and here's its secret. A neutron, left all alone, out on its own, does not last. Leave a lone neutron to itself, and after a while it simply falls apart. It turns into a proton and sheds the difference. And that difference it sheds is exactly the little extra weight I had you pocket, because nature, offered the chance, will roll downhill toward the lighter thing. The heavier block decays into the lighter one. Neutrons on their own are perishable. Protons, being the lighter, are endlessly patient. A lone proton just sits there, apparently forever, with nothing lighter to fall into.
So one of my two ingredients is going off. The neutrons are quietly rotting while I sit here waiting for the furnace to cool enough to cook.
That's the picture precisely. The clock is running on the neutrons from the very start. And remember, we have to wait. We have to let the furnace cool down through the too hot phase before any cooking can begin. And all through that waiting, the neutrons are quietly defecting, one by one, turning into protons.
So by the time the window finally opens,
The two blocks are no longer anywhere near even in number. There are far more protons than neutrons left by then. The protons have been winning the whole long wait because their rivals keep quitting the field and joining them.
the neutrons are literally deserting to the other team, while we stand about waiting for the oven to cool. That's bleak. So when cooking finally kicks off, I've got a great crowd of protons, and only a thin band of neutrons still standing.
A great crowd of protons, a thin band of neutrons. Now, the cooking. To build one helium nucleus, you need two of each, 2 protons, 2 neutrons. So every helium you make spends 2 of your precious, scarce neutrons.
And here's a thing I don't follow. Why do the neutrons all end up in helium, tidally paired off? Why don't they get scattered about? A few stuck in the half-built bits, a few left loose, some here, some there.
Because helium is a special place to be. Of all the little bundles you could make from these blocks, that particular one, 2 protons, 2 neutrons, is unusually snug, deeply, comfortably bound. It's a basin the cooking rolls downhill into. Once the blocks can reach it and it can survive the heat, that is overwhelmingly where they settle. So very nearly every neutron still standing gets swept up and locked away inside a helium nucleus. Used up almost to the last one.
So the neutrons set the ceiling. However many of them survived the weight, that's the most helium you can possibly make, because each helium demands its own pair of them.
You've got it whole. The scarce ingredient sets the ceiling. Every surviving neutron gets paired off into that snug helium basin, and then you look round at what's left over. And what's left over is that great crowd of surplus protons, the ones who never found a neutron to pair with. And a lone proton is
Hydrogen, the leftover block, the default, so the hydrogen is just the protons that couldn't get a dance partner.
the protons that couldn't get a dance partner. That is the whole of it. And because the protons so badly outnumbered the neutrons by the time the music struck up, you're left with a great deal of leftover hydrogen and only a modest helping of helium. When you weigh the harvest up, it comes out to roughly 3/4 hydrogen, about 1/4 helium. That's the split. And it isn't an accident, and it isn't a dial anyone tuned. It falls straight out of a rotting neutron and a closing window.
Roughly 3/4, 1/4. And that's not just our own back garden. That's everywhere. The whole universe came out of those minutes carrying the same recipe.
Everywhere. Every corner of it went through the same furnace, the same cooling, the same closing window at the very same time. The recipe is universal because the kitchen was universal. There wasn't a hydrogen district and a helium district. There was one furnace, and it was all of space. Which is why, when we look at the oldest gas in wildly different directions, as far apart in the sky as you can point, it all carries that same 3-to-1 stamp. One kitchen, one recipe, printed on everything.
And does that recipe still hold today, though? The universe has been busy making stars for ages since. Haven't they been quietly topping up the helium the whole time?
A little. Stars do make some helium as they burn, and they have been at it a long while now. But it is a topping, not the loaf. The great bulk of the helium in the universe, most of it by far, is furnace helium. Primordial, straight from those first minutes. The stars have only sprinkled a little more on top of a cake that was baked before the first of them ever lit.
Now, before you carry on, I want to say what I'm sure happened next, and you can tell me how wrong I've got it. The furnace makes hydrogen and helium. It's hot, it's cooking, it's clearly good at this, so why does it stop at helium? Why not just keep going, fuse the helium into something bigger, and that into something bigger again, and climb all the way up the ladder? Carbon, oxygen, iron, gold. Cook the whole set while the oven's still lit.
That is precisely the question, and I could hug you for asking it in that order, because it's the great trap of the whole night, and nearly everyone tumbles straight into it. It feels so obvious. Hot furnace, keep cooking, make the lot. And it's wrong on 2 counts at once.
2 counts. Go on then, tell me why my beautiful full set of elements doesn't come out of the oven.
The first count is the window again. Remember, it's slamming shut. By the time you've clawed your way up to helium, the furnace has already cooled and thinned so far that there's barely any cooking left in it at all. You spent your whole handful of minutes just getting to helium. There's no time left on the clock to climb any higher. The oven's going cold under your hands.
So, even in principle, you've simply run out of oven. Fine, that's 1 count. What's the second?
The second is a genuine roadblock, and it's a beautiful one. To climb past helium, you'd need a firm next rung to stand on. A nucleus just a touch heavier than helium that holds together long enough for you to build on top of it. And right there, just past helium, the ladder has a rung missing. The little nuclei you'd make on the very next steps up fall to bits almost the instant you make them. There's no firm stepping stone there to carry you any higher.
A missing rung on the ladder, right at the spot where your foot needs to land. So even given all the time in the world, you couldn't easily get past helium anyway, because the next step just crumbles under your boot.
Crumbles under your boot. So there you are, a furnace running out of time, and a ladder with its lower rungs knocked clean out. Between the two of them, the cooking stalls. It makes the lightest things, and it quits.
The lightest things and quits. So, hydrogen, helium, and then nothing, a clean stop.
Almost a clean stop. Not quite. A few things get caught halfway. Picture the cooking as an assembly line that gets switched off mid-shift. Most of it finished the job, hydrogen and helium, but here and there you find a half-built piece that never got completed before the lights went out.
Half-built? Half-built like what?
A whisper of the very next lightest things. A trace of what you might call heavy hydrogen, a proton with a single neutron stuck onto it. One step along the road to helium that just never took the next step. Deuterium, that one's named. And a faint dusting of the rung just past helium, a little lithium, the tiny bit that squeaked across the missing rung before the window shut. But we are talking whispers here. Traces. A pinch of these in a whole ocean of hydrogen and helium.
So the honest inventory of the first 3 minutes reads, overwhelmingly hydrogen, a good slug of helium, a whisper of the next couple of things, and then, essentially nothing heavier, full stop.
Essentially nothing heavier, full stop. That is the entire harvest of the first 3 minutes. The 2 lightest elements in that rough 3-to-1 split with a trace of the almost as light. And nothing else. Nothing at all.
Then I've got a problem, a personal one, because I am not made of hydrogen and helium. I mean, there's hydrogen in me, sure, all that water, but I'm also carbon. I'm oxygen. There's calcium in my bones and iron in my blood. And you're sitting there telling me that the universe, in its one and only great cooking session, made none of it. So where did I come from? Where's the carbon? Where's the iron? Where's the gold in the ring on my finger?
And there it is, the loose thread I most wanted you to reach out and pull. You've just put your finger on the single biggest gap in tonight's story, and you found it by looking down at your own hand. The Big Bang did not make you, it made your water. The rest of you, the carbon, the oxygen, the calcium, the iron, the gold, was made somewhere else, later, and far more slowly.
Later and slower. Where though? If the hottest furnace there ever was couldn't manage it, the whole universe on full blast, then what on earth could?
The stars. But that's a whole night of its own, and I won't spend it now. I only want to plant it, so it's waiting for us when we come to it. Remember I told you the furnace was hotter than any stellar heart, but it had only minutes. A star is the other way about. A star is cooler than the furnace ever was, but a star has all the time in the world. Ages upon ages of patient burning. And it turns out patience is the one thing the furnace never had.
So the fast furnace made the light stuff in a rush, and the slow stars, taking their time, made the heavy stuff. The Big Bang did the quick, easy cooking and left the hard, patient cooking to the stars.
The quick, easy cooking and the long, patient cooking. And every heavy atom in you, the iron, the calcium, the carbon, is a little morsel of that slow, stellar work, made long after tonight's 3 minutes were finished and cold. So you're a strange blend when you sit with it. Your hydrogen is primordial, cooked in the first minutes, older than any star that ever shone. And the carbon, the oxygen, the iron, every heavy scrap of you is much younger, forged inside stars that had to live and die to make it.
Half of me older than the stars, half of me cooked in them. That's going to sit oddly at breakfast tomorrow. All right, I'll hold the star business, but you should know it's going to nag at me the whole way home.
Good. Let it nag. Now, you've been very patient and you've earned the best part. Because I can feel the objection you've been politely sitting on all night.
You can you? Go on then, tell me my own objection.
You're thinking, this is a gorgeous story. Rotting neutrons, a closing window, hydrogen and helium in a 3-to-1 split, a whisper of the half-built, nothing heavier. Lovely. And here's your trouble with gorgeous stories about the first 3 minutes of time. Nobody was there. There's no photograph of it. I told you myself, the baby photo comes hundreds of thousands of years later. This all happened before there was even any light to see it by. So how is any of this science, and not just a beautiful bedtime story you've talked me into?
That is precisely my objection, word for word, and now I'm faintly unnerved that you had it loaded and ready. So, go on, how could anyone ever check a story about the unwatchable?
Now you've asked the question that turns tonight from a fairy tale into a triumph. And it's the best question you've put to me all season. You're quite right that we cannot photograph the first 3 minutes. But here's the thing. We don't have to, because the furnace left a receipt.
A receipt.
A receipt. Think about what the story predicts, really predicts, out loud, in advance. It says this: whatever gas in the universe is truly pristine, gas that formed straight out of the fireball and has never once since been inside a star, never been touched by that later, heavier cooking, that gas must show exactly the recipe of the first 3 minutes. Roughly 3/4 hydrogen, about 1/4 helium, a particular whisper of the heavy hydrogen, a particular faint trace of lithium. Those exact proportions, and no carbon, no oxygen, no iron. That's a prediction. It sticks its neck right out on the block.
So the test is, go and hunt down some of this virgin gas no star has ever cooked, and read off what's in it. And if the story holds, it should read back the recipe of the first 3 minutes.
That is the test, exactly. Go hunting for the oldest, most pristine gas there is. Clouds that have sat all but untouched since almost the beginning, that no star has ever fouled with its heavier ash. And measure what they're made of, right down to the last part.
And? Don't you dare pause on me there, and?
And it matches beautifully. We went and found the most pristine gas in all the universe, the least touched, the nearest to raw, and we read off its recipe. And there it was. Roughly 3 parts hydrogen to 1 part helium, the right whisper of heavy hydrogen. The recipe that fell out of a rotting neutron and a closing window, written into real gas we can genuinely measure, a whole universe and an unthinkable gulf of time away from the minutes that first mixed it.
Hold on, let me make sure I've got the true size of this. You wrote down what must have happened in the first few minutes of all of time, minutes nobody watched before there was so much as light to watch by, and you turned that into one specific, checkable claim about the exact mix of the oldest gas there is. And then you went and looked, and the gas agrees with you.
The gas agrees, down to the fine grain of it.
And is it only the helium that lines up? Because one number matching I could just about wave off as a fluke. You fished until you found a fit.
Ah, and that's the sharp end of it. And this is why it's a triumph rather than a coincidence. It isn't one number. The helium is one prediction. The whisper of heavy hydrogen is a separate prediction, worked out a wholly different way, and it lands just as squarely on the mark. Two different substances, reasoned out two different ways, from the same handful of minutes, and both turn up in the pristine gas exactly as the story promised. But I'm going to be honest with you tonight, because there's a third, the lithium, and the lithium will not come to heel.
So two roads, set off from different places, arrive at the very same crossroads. And the third, the lithium, comes in somewhere else altogether.
Two roads that had no business agreeing, arriving at the very same spot. And that is precisely the moment a careful person stops calling it a story and starts calling it a fact. One match you could wave off as a maybe, two independent matches is a fingerprint. But the lithium, the furnace should have left behind a certain trace of it, and when we go to the pristine gas, we find a good deal less than the recipe swears there ought to be. We predict more than the oldest gas will ever show us, and no amount of care has closed the gap. It even has a name, the lithium problem, and it is still sitting there, open, an honest thorn in a beautiful story.
But hang on, to predict those three numbers in the first place, you would have to know the furnace's habits cold. How fast a neutron rots, how keenly the blocks fuse and clamp. How could anyone possibly know that about a furnace that shut down before there was even any light?
Because the blocks have not changed since. A neutron rots at the same steady rate on a laboratory bench today as it did in the first minutes. These little nuclei fuse just as keenly here and now as they did then. We measure their habits right in front of us, in the present, and carry those very same rules back into the furnace and let them run. Nothing about the early universe had to be invented. It was all measured, just measured rather late.
A fossil of the first 3 minutes, written in hydrogen and helium, and signed twice over, clear as day, with a third mark still smudged and argued over. I'll be honest, I came in here tonight all set to catch you inventing a tale about the unwatchable, and instead you've handed me a receipt for it. 2 clean signatures and an honest puzzle. That's annoyingly good.
I'll take annoyingly good and count myself lucky. But let me push the receipt one step further because it gets better still, and it sets up something I'm going to need next week. That whisper of heavy hydrogen, the half-built stuff, the proton with a neutron that never finished the climb. The exact size of that whisper isn't a random thing. It's a dial.
A dial. A dial reading what?
How crowded the furnace was. How much ordinary matter there was in it to cook with in the first place. Think it through with me. If the furnace had been packed very densely with blocks, protons and neutrons crammed elbow to elbow, then nearly every bit of half-built heavy hydrogen would have quickly found a partner and finished the trip on up to helium. Almost none would be left stranded halfway. So a crowded furnace leaves behind only the faintest whisper of heavy hydrogen.
And a thinner furnace, fewer blocks, more elbow room, leaves more of the heavy hydrogen stuck halfway, because the pieces couldn't find each other quickly enough to finish the job before the window slammed.
Exactly right. So the amount of leftover heavy hydrogen is a direct readout of how crowded the furnace was, which is to say, how much ordinary matter the whole universe holds. Measure that faint whisper in the pristine gas, and you have weighed all the ordinary matter in creation. From a trace of half-finished hydrogen, you get the grand total of the ordinary stuff, all the protons and neutrons in the entire universe.
So the first 3 minutes didn't only leave us a recipe, they left us a set of scales, a way to weigh all the ordinary matter there is.
A set of scales. And you keep those scales in your pocket because next week I'm going to hand you something to weigh with them that does not add up at all. But not yet.
You and your not yet, fine, but before we get anywhere near next week, can I circle back to something that's been quietly gnawing at me this whole time? You keep saying the furnace was full of these blocks, protons and neutrons, as though that's just the natural place to start. But where did they even come from? Why was there any stuff in the furnace to cook at all, and not just fire? Just light and nothing in it.
You found the trapdoor underneath the trapdoor. And I have to be straight with you here, because this is a place where the honest answer is, we are not sure. But let me tell you what makes it so strange, because it's one of the deepest open puzzles in the whole of physics.
Go on. I like it when you go uneasy on me. It means we're standing near something real.
In that fierce early heat, matter did not come alone. Every kind of block, every proton, every neutron, has a mirror image twin, a sort of anti-version of itself, the same but opposite. We call it antimatter. And in that heat, matter and antimatter were being made together, hand in hand, in very nearly equal amounts. Made together, and here's the sting in it, when a piece of matter meets its own anti-twin, the two annihilate. They vanish, both of them, in a flash of pure light. Perfect mutual destruction.
So if the furnace was making them in equal amounts and they wipe each other out on contact, then they should have wiped each other out. All of it, every last block should have met its anti-twin and gone up in a puff of light.
By every right, yes. The books ought to have balanced perfectly. Everything cancels, and you're left with a universe of nothing but light and not a single block of matter anywhere in it. No protons, no neutrons, no gas to cook, no stars, no planets, no you. Just light forever, and nobody there to see it.
But that's plainly not what happened, because here I sit, made of blocks, asking you about it.
Here you sit, which means the books did not, in the end, quite balance. For every vast crowd of matter and antimatter pairs that met and annihilated, there was left over the tiniest, faintest surplus of matter, a hair more matter than antimatter. And when the great annihilation was finally done, and nearly everything had cancelled away to light, that thin surplus was all that remained. Everything solid in the universe, every star, every planet, every atom in your body, is built out of that leftover sliver. The crumbs that had no anti-twin left to cancel with.
So we're the crumbs. We're what was left on the plate after the universe finished eating itself.
We are the crumbs. Everything you have ever seen or touched or loved is the rounding error in a very nearly perfect cancellation. And, by the by, the reason the meeting of matter and antimatter turns into a flash of light at all is that same coin of Einstein's from earlier tonight. Matter and light, two faces, one able to become the other.
Two faces of the one coin come back round again. All right, but then why was there a surplus at all? Why a hair more matter than antimatter instead of a dead-level split that leaves nothing behind but light?
That is the puzzle. And I won't dress it up for you or sell you a comfortable answer. We don't know. There must have been some faint thumb on the scale, very early, tipping it a hair toward matter over antimatter, But what did the tipping, and why, is genuinely unsettled. It's an open door, one of the real ones.
I appreciate you not pretending on that one. It's a strange thing to have to sit with, that the reason there's anything at all, rather than nothing, is a leftover we can't yet explain.
It's one of the honest edges of the whole subject, and there are a few of them, and we'll walk right up to each before this season is out. But for tonight, take the surplus as given. However it got there was ordinary matter in the furnace, and the furnace cooked it into the recipe we've spent all night chasing.
Then let me try to hold the whole night in my 2 hands at once, because I want to be sure I've actually got it, and I'm not just nodding along. First few minutes of all of time, every scrap of space a furnace, hotter than any star's heart, a soup of 2 blocks, protons, which are hydrogen for free, and neutrons, which are perishable and keep rotting into protons, while we wait for the thing to cool.
Good. Keep going.
The furnace cools as it expands, too hot at first to hold anything together, then for one narrow window of a few minutes, just right. In that window, nearly every surviving neutron gets locked into that snug helium basin, and because the protons so badly outnumbered them by then, we're left with a great deal of leftover hydrogen and only a modest amount of helium, the rough 3-to-1. A whisper of the half-built, and nothing heavier at all because the window slammed shut and the ladder had a rung knocked out of it.
That's it. That's the whole of it, and you've told it back to me straighter than I told it to you. And the receipt, you've got the receipt too.
The receipt. The oldest, most pristine gas we can lay hands on reads back that recipe. The helium and the heavy hydrogen signed clean and clear. The lithium still off and still argued over, which turns the whole unwatchable business into a prediction that came true, loose end and all. And the faint whisper of heavy hydrogen doubles as a set of scales, weighing all the ordinary matter there is.
All the ordinary matter there is. And that means something rather grand when you stand back from it. For the first time, we can begin writing out the recipe of the whole universe. Not the recipe of the first 3 minutes, but of everything, here and now. And tonight, we've measured the very first ingredient on that list. The ordinary matter. The stuff that shines. The stuff we can see.
The first ingredient. You say that as though you already know there's a whole list of others coming.
Oh, there is a list. And here I get to spring the thing I've been carrying in my pocket the entire night.
I knew it. There's always a thing in the pocket with you. Go on, spring it.
You just said it yourself, clean as anything. We've weighed all the ordinary matter in the universe. All of it. Every proton and neutron the furnace ever cooked into hydrogen and helium. The stuff of gas, of stars, of planets, of people. We've counted it. So here's what I want you to go and do with that count next week. Find a galaxy, a great whirling pinwheel of a thing, 100,000 million stars turning together, and watch how fast it spins.
Watch it spin. And what does the spin tell me?
How much weight it must be holding, because it takes weight and the pull of it to keep a thing whirling that fast from simply flinging itself to pieces. Work out the spin and you've weighed the galaxy. And then add up all the ordinary matter you can actually see in it. Every star, all the gas, all the hydrogen and helium the furnace made.
And I'm guessing from the particular look settling onto your face right now that the 2 numbers do not match.
They're not even in the same country. Count up every scrap of that cooked hydrogen and helium, all the ordinary stuff that stars and planets and you are made from, the entire harvest of the first 3 minutes, and it is nowhere near enough. Nowhere near enough to hold a spinning galaxy together. The galaxy whirls so fast, it ought to be flying apart in every direction, and the ordinary matter cannot begin to account for the weight that's holding it whole. You could pour in every atom the furnace ever made, count it twice over for luck, and you would still fall hopelessly, laughably short.
So the recipe we were so proud of tonight, the hydrogen, the helium, the ordinary matter we finally learned to weigh, that's not most of what's out there, not even close to most of it.
Most of the weight of the universe is something else entirely. Something the furnace never cooked and never could. Something that doesn't shine, doesn't glow, casts no light at all, and yet reaches out and holds the galaxies together by its pull. Something dark. And that is exactly where we go next.
The first 3 minutes cooked all the ordinary matter there is. And it turns out ordinary matter is the small part. The part we can see is the part that barely counts. You've spent a whole night teaching me the recipe of the universe, and your parting gift is that the recipe is mostly missing from the page. I'm going to lie awake on that one. So, weigh a galaxy by its spin, and most of it is a stranger we can't see. All right, bring me the stranger next time. Good night.